Hey guys, hope you're all doing well. In the last video, we further tuned our model by reducing the learning rate and adding an extra layer of depth to our model. While we saw a significant increase in accuracy, there was also signs of overfitting, which means that our model was effectively trained to classify the training data. It did not generalize well to the validation data. To fix this overfitting issue, let's introduce one more technique to improve the model training process. This last technique we are going to introduce is referred to as data augmentation. If you have previously taken my self-driving car course, chances are you're already familiar with the basic theory behind data augmentation. But in any case, this is the process by which we create new data for our model to use during the training process. This is done by taking our existing data set and transforming or altering the images in useful ways to create new images. So for example, we could have a typical traffic sign image such as this stop sign image, and now we can take this image and transform it to create a different image representing the same stop sign. An example of a transformation could be rotation, or it could be something as simple as zooming into the image. Or it could even be a combination of both these transformations. These newly created images are referred to as augmented images because they essentially allow us to augment our dataset by adding new data to it. Now this process might initially appear to be redundant. A stop sign is still a stop sign at the end of the day, so why would our model benefit from looking at a rotated picture of the same stop sign or even a zoomed-in picture of the same stop sign, you might ask? Well, the answer to that would be variety. The reason this data augmentation technique is useful is because it allows our model to look at each image in our data set from a variety of different perspectives. This allows it to extract relevant features more accurately and allows it to obtain more feature-related data from each training image. How will we use data augmentation to reduce overfitting? Well, we know that overfitting occurs when your model is too closely fit to the training set, making it more difficult for the data to generalize to new examples that were not present in the training set. The first thing one would think of is to add more data, use a larger data set. Using a larger data set can also help to reduce overfitting, as the network must now be flexible enough to account for more data, making it harder to memorize idiosyncratic features and more likely to generalize. However, you don't always need to start collecting new images and adding them to your datasets. We can use data augmentation, which simply introduces minor alterations to our existing datasets, such as darker shading, flips, zooming, rotations, translations. Our neural network will interpret them as separate, distinct images, increasing the amount of relevant data in our datasets. By increasing the amount of relevant data, not only does this work to reduce overfitting, but it prevents your network from learning irrelevant patterns and boosts overall performance. Alright, so back to our code, let's work towards augmenting our dataset. The variety of augmentation transforms can simply be found on the PyTorch documentation. We won't be making use of all of them, simply enough of them to improve our model performance and give you an idea of how they work. PyTorch makes defining these transforms really easy, as they can simply be done inside of transforms.compose, and then applied to our training dataset. So what we'll do is we'll have a transform for the validation set. We'll leave that as it is, leave it as transform, and we'll copy and paste it. And we will rename, whoops, not here. Copy and paste it over here, and rename it to transform train. And we will apply the transformations from this variable to our training dataset, just the training dataset. And we will only make use of 4 transformations, which, as you'll see, will add sufficient variety to our dataset and will allow the training process to be much more effective. The first alteration we introduce to our dataset is just a random horizontal flip. Transforms.random horizontal flip. We can also rotate our images by a certain angle. Transforms.random rotation. The first argument denoting the angle, which we will simply leave as 10. And to add even more variety to our data set, we can introduce affine type transformations. Affine type transformations, which you may have already come across, generally represent simple transformations that preserve straight lines and planes with the object. Scaling or zooming is a transformation that fits this category. Translation, shear are also transformations that fit this category. So what we do is we write transforms.random affine, and the first argument is the degrees, which we will set as 0 to deactivate rotation. One should note that we have set random rotation as a transformation. Next, we have the shear transformation, which one can denote as shear is equal to. In plane geometry, a shear mapping is a linear map that displaces each point in a fixed direction by an amount proportional to its signed distance from a line that is parallel to that direction. It can be visualized here. As you can see, shear is possible in both the x and y direction, which adds some variety to the transformation. This transformation is defined using shear intensity, which simply refers to the magnitude of the shear angle in degrees, as seen in the image above. I have found setting a shear equals to 10 provides really good results. And now scaling is another transformation that fits the affine category, so we can use the scale argument and use a tuple to define the range of zoom that we require. In our application, for improved feature extraction, we can create datasets that are both scaled in or scaled out. We can define a lower and an upper limit of 0.8 to 1.2. This is simply going to scale images to 80 or 120% of their size. It will select a random percentage of zoom within our defined range for each new augmented image. Now we can move on to our next augmentation, creating new augmented images with a randomized variety of brightness, contrast, and saturation. We do this by writing transforms.color jitter with a brightness is equal to, and we specify a value, or a jitter value I should say, of 0.2, establishing a range of how much to jitter the brightness values. From experience, I have found that the model reacts better to a relatively low brightness factor. We will assign that same factor to both contrast and saturation, both of which will equal 0.2 for contrast as well. And now we have effectively defined our image transformations, and we've defined its capabilities. We have just defined the transformations that can be applied and the range of these transformations. We can now assign these transformations to our training set, which we already have done, which will serve to augment our training data in many different ways, adding necessary variety to our data set, such that some images will be zoomed in or out, while others will be rotated, sheared, or shifted. For the most part, many of these images will be transformed in more than one way to ensure an effective augmentation process. And this will be quite a useful training tool for our model. Let's go ahead and see the effect by running our code. Runtime, run after. Invalid syntax transforms the random rotation. And I seem to have forgotten my commas everywhere. Let's make sure we don't do that. Trying this again. All right, having trained our model with data augmentation this time around, we can witness a reasonable improvement over our previous model. Increasing the amount of relevant data, augmenting our data set with random rotation, zooming in, zooming out, jittering with the colors. These minor changes were interpreted as distinct images, expanding the variety in which the original image is received by the neural network. And it was well received, as not only did it reduce overfitting, but our validation accuracy for the SciFar dataset is at an all-time high, such that the model is now better generalizing itself to it. This is really good to see, and looking at our graphs, we can see that our issue of overfitting has been resolved. What would be interesting to see, however, is to check and see if our neural network can classify the image of a dog that it wasn't able to earlier. Recall before it predicted that this dog was a cat. So let's see what it predicts this time around. Run, and running the following prediction. It predicts it as a dog. This is really good. Clearly an improvement to our last model. We can try even more images from the web. From experience, I have found that deers are hardest to classify. You know what? Let's start with this frog. Copy image, address, right onto our project. All right. Predicts that as a frog. Let's try deers as promised. We will try the following image. Copy image address, right onto our URL variable. Running the following cells, it predicts it as a deer. All right, just to challenge our network, let's try a hornless deer. Hornless deer. That one should be pretty hard to classify. Let's give it a try. Copy image address. And it gets this one correct as well. This is really good to see. And finally, testing this on our validation. All right, and it predicts all of our images correctly. This can vary. In your model, it might only predict one of your images incorrectly, or maybe two, but this is fine because it's worth noting that the performance of our model is quite reasonable and does not overfit. While we could further perform regularization techniques, tune the architecture complexity, and further adjust model parameters, there are a plethora of ways to approach honing in on the optimal model parameters. But I want to give you the opportunity to validate the skills you've learned so far in this course and challenge yourself to create a model that can achieve a higher accuracy without overfitting. Feel free to share your results on my Facebook page, which you can access through my Udemy page. I would love to see the results that you come up with and further advise you on how you can better tune your model. All right, we will conclude our discussion on the CIFAR 10 dataset, as in the next section, I will show you how to make use of state-of-the-art pre-trained models to classify your own datasets. I will see you then.